Hi, and welcome to Module 5 of Lecture 4, the final module of the final lecture for this course. Like all final modules in a given lecture, this will be a problem session, but unlike previous problem sessions, we're not going to focus on doing sample problems. Instead, we're going to go back through some of the material we talked about in Lecture 4 and elaborate a little bit upon it. So the first topic I wanted to talk about is interaction terms. So if you recall, when we discussed what an interaction term was, the model looked kind of like this. So it had one independent variable x1, and it had a second independent variable x2, and then it had the product of x1 and x2, all with their own coefficients. Now we used interaction terms with this product term when we wanted to capture situations in which the effect of x1 on y was itself affected by x2. In other words, x2 conditions the effect of x1 on y. Then we went further and we identified what the marginal effect of x1 on y was. In other words, we identified the total effect of x1 on y. We wrote that like this, with a derivative, a partial derivative, that represented the rate of change of y with respect to x1 holding other variables constant, in this case holding x2 constant. And we did that out and we got that this was equal to beta 1, the coefficient on x1, plus beta 3 x2, which ends up being the coefficient on x1 in the product term when you hold x2 constant. So this is what we got. This gives us in a sense, point prediction for any value of x2. We can predict the estimated value of the marginal rate of change of y with x1. So for instance, if I were to make a plot here, and here's the 0, and let's say I assume beta 1 is negative and beta 3 is positive. What that means is when beta 1 is negative, if I plug in 0 for x2, then beta 1 gives me the y-intercept. So here's beta 1, it's negative. Here's the 0 line. And if beta 3 is positive, that means this line increases. Okay. With x2, which is over here on this axis. Now what am I graphing here? I'm graphing not y, I'm graphing the rate of change of y as a function of x1. So I'm graphing the marginal rate of change of the dependent variable y with respect to the independent variable x1 as a function of the other independent variable x2. So this is what this says. This is basically as far as we got before. What we didn't talk about very much was uncertainty. Now because beta 1 is going to be an estimate of beta from our sample, and beta 3 is also an estimate of beta 3 hat is going to be an estimate of beta 3 from our sample, we're going to have uncertainty inherent in our estimate of the marginal rate of change of y with x1. How do we capture that? Well, I'm not going to go through here and discuss how to, in general, capture the marginal error on this compound term. Rather, I'm just going to point out that to figure out how to deal with uncertainty, we must incorporate not just uncertainty in beta 1, and not just uncertainty in beta 3, but uncertainty in the entire equation here. The entire underlying equation has inherent uncertainty in it. We have to take that into account. The way we typically do that is by drawing on this plot, on this marginal effects plot, as it's called, a 95-degree confidence bound, a set of 95-degree confidence bounds. So let's do that over here. So let's say, this is just a random example, I'm making it up. Let's say it looks like this. What do these confidence bounds mean? Well, it means if I'm within the dotted region, then I'm 95% certain, right? I have 95% confidence that the true value of the marginal effect lies within this dotted region. That's what it means. The same thing as confidence intervals we discussed before. What does it mean for us here? That means if my null hypothesis is that there's no effect of x1 on y, so the marginal rate of change of y with respect to x1 is 0, then I can't reject the null hypothesis if the 0 line here falls within my 95% confidence bounds. For the same reasons we discussed before, when we did all the stuff we did before with hypothesis testing. If a 0 falls within my 95% confidence interval, I can't reject the null hypothesis. So what we see here is my ability, in this case, to reject the null hypothesis depends on the value of x2. If, and this is the cutoff here, where the confidence bounds cross the 0. If I'm on this side of the confidence bounds, to the right of that cutoff, then, to the right of that cutoff, then the confidence bounds are always above 0. So I know with 95% certainty that I can reject the null hypothesis that x1 has no effect on x on y, and instead posit a positive effect here that they seem to be positively correlated at the 95% confidence level. Which means we expect here, we have support for the notion that increasing x1 increases y in this range of x2 only. For the other range of x2, from 0 back, from that cutoff point back to 0, the 0 line is within the confidence bounds, so we cannot reject the null hypothesis that x1 affects y. So we see here is we have interaction terms. Whether or not things are going to be significant predictors or not will depend upon the direction, where you are on the line with respect to x2, the other variable. Okay, so let's do another example really quickly. I'll do a couple more actually. If we had beta 1 as positive and beta 3 as negative, it would look like this. Here's beta 1, and here would be the line. And again, we could draw confidence bounds. This one, I should have made it all dotted, sorry. This one, let's see how we do this. This one might have a little different behavior. In this case, the 0 is within the confidence bounds for all values greater than the cutoff, but for values less than the cutoff, it's not within the confidence bounds. So for this case, we would say that we would observe a positive effect of x1 on y, right? We could reject the null hypothesis. There's no effect at a 95% confidence level, but only for low values of x2 and not for the high values of x2. That can change based on the confidence bound, based on our errors. If, for instance, we had these errors instead, then we can never reject the null hypothesis because the 0 line falls within the confidence bounds all the time. Conversely, if we had a situation like this, say, where we had a positive beta 1 and a positive beta 3, or negative both if you wanted to, and the confidence interval looked like this, then we can always reject the null hypothesis for all values of x2. So in practice, it depends upon what your confidence bounds look like, which depend on the errors of this equation up here. The errors inherent in the total marginal effect of x1 on y. Now, before I move on, a couple of small points. You saw that I kept drawing the confidence bounds being more narrow, or I tried to at least, in the middle of the x2 range. That's not guaranteed. That's not required. You often see that because oftentimes your data will tend to have more data points for middle values of an independent variable than the extreme values. As we know before, the standard error goes down as you have more data points. So we see a smaller error around the middle of the x2 of the independent variable you're conditioning on often because you just have more data there, so the error gets smaller. Whereas for the extreme values of x2 here, you have less data, so the errors get bigger. This is common but not required. It's not part of the underlying theory. It's just because of the way data are distributed and what you have to work with usually in that case. Second, the nice thing about all this, there's two nice things. One is just by going through what we learned earlier involving the calculation of a marginal effect, we can actually figure out what this should look like and what the actual total effect of the interaction term should have, and understand exactly how to interpret the interaction term properly in terms of its effect on the marginal effect of x1 on y. That's not trivial. There's lots of historical mistakes that have been made in misinterpreting interaction terms. Two, because of that, in recent years, there's been a profusion of lots of different packages that you can access to do these plots, these kind of plots, these marginal effects plots in all different types of statistical packages. So in practice, what you would do is you have an interaction model, you have a package produce a plot like this, and then you can use this, what we've been discussing, to interpret it properly. So that's interaction terms. Now I'm going to go and I'm going to erase this and discuss very briefly a related topic, which is nonlinear regressions. Right? The regressions, linear regressions with nonlinear terms. Right? So we discussed earlier one where we had a quadratic term with the sleep and the grade example. And here we have two different coefficients, beta 1 and beta 2, and one applies to x, one applies to x squared. And we did the same analysis before, and we discovered that dy dx, I don't have partials here because there's only one variable, so there's no reason to have a partial, there's nothing to hold constant, there's only one variable, is going to be beta 1 plus 2 beta 2x. So just like before, we find that if we were to draw this out, and let's say beta 1 and beta 2 were both positive, then this would be beta 1, and this would be the marginal effect of x on y, and this would be x, and we'd find that this would be increasing if both beta 1 and beta 2 are positive. And if beta 2 are negative, you'd have this decreasing, and so on and so forth. And again, you'd also have errors that you could see, and you could determine whether or not the marginal effect of x and y was significantly different from 0 at all points in x or only some points in x. Same exact stuff we just talked about in the previous, not slide, but whatever, the screen. So I'm not going to go over it again. Everything else applies as before. Note, though, that the reason this is a straight line, whereas this thing looks more like this, is this is graphing y, right? And if the graph of y against x is quadratic, it's a nonlinear curve, the marginal effect is linear because the derivative of a quadratic term is a linear term. It's a line. Okay. Don't want to go into any more detail on that, but it's just all the same ideas we just saw for interaction terms, just applied over here. Okay. Okay, and now I want to erase this one more time. I want to talk briefly about time series. One thing we discussed earlier in the lecture was that if I have y of sub t, so I have a time series with data across time, and I have a dependent variable at some time t, then we can capture the dependence on earlier parameters and earlier times by lagging the dependent variable, which means I include a constant coefficient lambda here, multiply it by the dependent variable at the previous time, and then add my normal regression model to it. Here, xt can be a single variable, or many variables, but we'll consider it a single variable for convenience right now. So the dependent variable at time t is dependent on the previous period's dependent variable, plus function of this period's independent variables. And we said there was that this effectively incorporated earlier independent variables into the mix. But we didn't really talk through how that worked. I kind of hand waved through it, but I didn't show you. So I'm going to show you now very quickly. The way to do that is just by substituting back in for y of t minus 1 recursively. So y of t minus 1, by just changing the subscripts in this equation, must be this. And y of t minus 2, similarly, will look like this. All I'm doing is moving back the time by 1 every time. And so on and so forth. So what does this leave you with? Well, if I want to, I can write this out, and first I get y of t equals alpha plus beta t plus lambda, and I'm going to plug in this up here for y of t minus 1. Okay, and I can multiply out and collect some terms, and I get alpha times 1 plus lambda, and I get beta, I dropped an x there, sorry, x sub t, beta times x sub t plus lambda times x sub t minus 1, and I get lambda squared y of t minus 1, t minus 2, sorry, and I can plug in t minus 2 for that, and then I do it again, and now I will get alpha plus 1 plus lambda squared. I'm gonna go a little quicker here and skip a step. You can do it at home and add the step in if you want. All I'm doing is plugging in this thing for this thing and collecting terms again. And I get this. So the same thing as before, still there, but now a lambda squared times x of t minus 2 from this term over here. And a lambda cubed of yt minus 3. And I could go on and do this over and over and over again as many periods as I had in my data. And you can see the pattern here, I think. This first thing is a constant, so we ignore that. But we have over here is a series of xt's. The first xt is not multiplied by anything. The second xt is, except for beta, the second xt is multiplied by lambda, the third by lambda squared, and so on and so forth all the way back. If lambda is less than 1, then 1 is greater than lambda, is greater than lambda squared, is greater than lambda cubed, and so on indefinitely. So the constant I'm multiplying by each of the earlier independent variable instances is getting smaller and smaller and smaller. So that's the origin of the claim we made earlier, in that this kind of approach, in which you lag the dependent variable, incorporates earlier time periods independent variables, as we see here, but less and less as you go back further and further in time. So y of t equals beta times x of t, so it fully incorporates the present period's independent variable, plus lambda of x of t minus 1, so it incorporates the previous period's independent variable, but discounted effectively by lambda, which is less than 1. And the previous period is still that, x of t minus 2. So the previous period is still that independent variable, but now discounted by lambda squared, which is even smaller than lambda. And so on, and as you go further and further back in time, you include all the independent variables, but they're less and less relevant to a prediction of y at t. So we do include all previous periods independent variables, as we claimed, but they have decreasing effect on y at this period. Okay. So that was that. And now for the final kind of disconnected thing here we're going to talk about is the logit. And it's going to be very closely related to the thing we talked about for the interaction terms. We discussed logit at some length earlier in this lecture, and we said that for a single bivariate logit, for instance, looks like this. So it's basically the original regression term for OLS, but stuck in an exponent in the bottom of an equation. Now, what do we do with that exactly? And the reason we use this was because if I stick in x equals infinity here, and beta is positive, this thing's infinite. So this thing goes to 0, so you get 1. That's the maximum. If x is negative infinity, this is e to the infinity, so this bottom is infinite. This thing goes to 0. So it's the minimum 0, so the formula goes between 0 and 1, which enforces our probabilities to be between 0 and 1. Compare this to our earlier OLS, and we have alpha plus beta x. And the nice thing about alpha plus beta x was that we know that for 1 unit increase in x, we increase y by beta units. So it has nice, convenient interpretation. And that's the reason some people still use linear probability models. Even though you get weird probabilities sometimes, you also get nice interpretations. We said in this case, for the logit, you don't get nice interpretations. But we didn't talk about why and how exactly that worked. We can see why by using a little calculus here. If we take the derivative of this OLS, we just get beta. So that's great. It's nice and simple. And we know that the marginal rate of change of y with x is beta, which is what we said. If I increase x by 1 unit, I increase y by beta units. What about this logit? Well, when we haven't gone over how to differentiate this. If you know how to do this, great. You should do it as a practice. It's great. If you don't know how to do this, don't worry about it. I'll just tell you. This is going to be, and if you want to know how to do it, you can go check out the math camp that I've mentioned a few times now. This is going to be beta e to the negative alpha plus beta x divided by 1 plus negative alpha plus beta x squared. Now, this has some reasonable properties. If beta is positive, so if I increase x, I increase beta x, then I also increase the marginal effect of x on y, which is what we would expect. Right? If beta is positive, so is the marginal effect of x and y. But the rest of this term here, right, all this stuff over here, that's not just beta, is the complication. It's why we don't have a uniform increase in y with x. Instead, it depends on the value of x. As we saw in the examples we talked about, we discussed the Logit. We saw different changes between different values of x. It also is why actually if we had not just beta x, but if we had e to the negative, say alpha plus beta 1x plus beta 2x, we'd get interaction terms that matter in this case. It wouldn't, because these x2s would still be in our marginal effects. So just like before with the interaction terms, we'd get a marginal effect of x and y that depends on the other variable x2, like we saw before, and that would lead to differences in the marginal effects based on the value of x2 as well as x1. So in general, interpreting the Logit can be more complex substantively because it's not just a constant uniform beta increase for each unit increase in x. It's much more complicated, as we see. But the thing is, it's complicated in an understandable way. We can compute the actual marginal effect as we've done right here, and then we can use a computer or existing packages to estimate these substantive effects for us, and that these packages exist, and you can use them regularly to interpret your Logit's substantive effect and substantive marginal effect. All you have to do is keep in mind that it's not going to be simply beta, so you shouldn't say it's beta. You should instead use one of these packages to compute your marginal effect appropriately and report that instead of just beta. Okay. That's it. Those are just 4 different things I want to go through at the end to make sure you saw a little more detail about what we discussed over the course of the slides. But that is it. As I said, this is the last module for the last lecture. I hope you enjoyed the lecture. I thank you very much for listening, and take care. Thank you very much for listening and watching.